as was mentioned, I am doing a PhD at Bristol University, and I study X-ray binaries and active galactic nuclei, both of which are examples of some of the biggest and baddest objects in the night sky. They're both varieties of black hole. And I'm going to be talking today a little bit about X-ray emissions from black holes. So, first off, either a refresher or an introduction to what black holes are. At their very essence, they are just a region, a part of the universe from which it's absolutely impossible for any information to escape. They're characterized by an imaginary sort of surface called the event horizon. And the event horizon is the distance from the center of the black hole where the gravity is so strong that not even light can escape from it. So to give you sort of an idea of the scale of the gravity that we're talking about, in order for a rocket to leave the Earth, it has to have an escape velocity of 11 kilometers per second. So it has to be traveling 11 kilometers every second in order for that rocket to overcome the gravity of the Earth. In order for a light particle to leave a black hole from its event horizon, it would have to be traveling at 300,000 kilometers every second. So it would have to be traveling extraordinarily fast. And because light is the fastest thing in the universe, it acts as our natural speed limit for the universe. And so, because the gravity is so strong around a black hole, nothing can escape. Now, in order for a black hole to be formed, we need to have exactly the right combination of mass and size. So it needs to be something which is really, really, really massive, really heavy, and also be relatively small, or at least the right combination of the two. To give you, again, sort of an example of the kind of scales we're talking about, if there was to be a black hole which had the same mass as the Earth, it could only be 2 centimeters in diameter. So imagine taking the entire Earth, all of its mass, all of its matter, and compacting it down into something which was just 2 centimeters across. In those circumstances, we could create a black hole. How we find them, as I said, black holes, the gravity is so strong that nothing can escape from them. So surely that means it's impossible for us to see them. How on earth do we find them? One way is by looking at how things around them act. So just as, if you want to look outside your window and see if it's windy, you don't look outside and see the wind. Instead, what you might do is look outside and see leaves blowing on the trees, and that tells you that it's windy. Similarly, we can use the movements of stars, in some cases, to see where black holes should be because of the gravity of the black hole. And on the left-hand side is a diagram of a number of stars which are orbiting a black hole called Sagittarius A star, which is at the center of the Milky Way. We can also detect black holes through gravitational waves. So when 2 black holes collide and merge together, they give off a very strong gravitational wave signal, which we can then detect. And so, although there it's kind of a, well, we knew they were there, still, from what we know about physics, there must be a black hole left after that collision as well. And then lastly, we can use emission from accretion disks, which I'm going to talk a little bit more about later, in order to detect them. And here on the left is an image which I hope all of you saw over the last couple of years. It's the first picture of a black hole which was taken by the Event Horizon Telescope. So again, here we're not really looking at the black hole itself, but we're looking at what's around it. The black hole would actually be in this darker region in the center. And this glow around the outside is the accretion disk that's been captured by the Event Horizon Telescope. There are a couple of different types of black hole, and we classify them through their sizes. So theoretically, there are, or it is possible to create what are called micro black holes. These would have to be incredibly small ones with very high density. The best explanation for how they could have been created is through really tiny fluctuations in the density of the universe quite shortly after the Big Bang. Then stellar mass black holes, which are black holes with a mass of a few times that of our own sun. These would be created in at the end points, at the very ends of a star's lifetime. So if you have quite a large star, certainly quite a bit bigger than our own sun, as it starts to run out of fuel at the end of its lifetime and it starts to collapse under its own gravity, it can go supernova. Depending on how much there is left of the star after that supernova explosion, it could form a dwarf star, a neutron star, or if it's large enough, it could form a black hole. And finally, supermassive black holes are black holes which have millions or billions of times the mass of the sun. These objects are absolutely enormous, and it's believed that there's a supermassive black hole at the center of every galaxy in the night sky. To give you, again, some kind of idea of the scale, so I mentioned if we had a black hole, which was the mass of the Earth, it would be about 2 centimeters across. The largest black hole that we've seen so far is the black hole NGC 1277. Now, in order for light, so again, the fastest thing in the universe, to cross this black hole, it would take 4 days. In comparison, it takes 17 minutes for light to go from one side of the Earth's orbit to the other. Well, what's the point in X-rays? So X-ray astronomy is a relatively young science. This is because the Earth's atmosphere does a really good job of keeping out harmful radiation. So even though people have been looking up at the night sky with telescopes for hundreds and hundreds of years, it's actually only been in the last 100 years or so since we started being able to send things into space that we've been able to look at the night sky in X-rays. And on the right here is a picture of the NASA X-ray telescope, which is currently operating on the International Space Station. Now, the reason why X-rays are particularly interesting when looking at black holes is because of the accretion disk. So as matter gets closer and closer and gets sucked into a black hole by its gravity, it forms a disk around the black hole. And as the matter moves in towards the center of the black hole, it starts to lose its gravitational energy. And because of the laws of thermodynamics, being that energy can't be created or destroyed, that energy has to go somewhere. And it goes into making a very hot disk of gas and dust and plasma that circles the black hole. Now, as we get closer to the event horizon and closer to the center of the accretion disk, the disk gets hotter and hotter. So when you're relatively far out, it might only be sort of a few Kelvin or a few hundred Kelvin. As we get closer, it can get to thousands and tens of thousands. Now, the reason why this is important and why it's important for X-ray astronomy is because as the disk gets hotter, it has to radiate away lots of energy. And the best way of doing that is by sending out very energetic waves. So that's where a lot of our X-ray emission comes from. And the reason why this is really interesting is because we're getting closer and closer towards the event horizon. And as we get closer to the event horizon, the gravity gets much stronger. And so we're looking at sort of an area where we're really starting to test general relativity. And importantly, for a practical point, it's where things take less time as well. Going back to what I showed you before, that supermassive black hole NGC 1277 had a event horizon that was light days across. So it would take days for a glob of material in the accretion disk to orbit the black hole. Now, if we want to be able to observe things, and we want to be able to observe them happen lots of times, ideally, so that we can build up a really good picture of what's happening, it helps us if things happen quite quickly. So the further out we are, the longer processes can take. The closer we are into the middle of the accretion disk and the closer we are to the event horizon, the faster things can happen, which means that A, we've got a much better chance of seeing it happen in the first place, and B, we've got a much better chance of seeing it happen repeated times, and so build up a really good picture of what it is that's going on. And I'm going to quickly talk to you now about sort of a new and exciting phenomenon that's been discovered in some objects called AGN. So somebody briefly touched on AGN before, active galactic nuclei. These are very, very bright and very compact sources of X-rays located at the centers of galaxies. Now, when I say compact, I'm talking about compact in comparison with the size of the galaxies themselves, rather than sort of compared to other things. Okay, these are objects which are much bigger than the Earth, or even in some cases the solar system. So these are very, very bright X-ray sources, though. And recently, in the last 2 years, a few objects have been observed which show what are called quasi-periodic eruptions. So these are eruptions in X-rays which occur, so the quasi-periodic means they occur roughly regularly, and actually what makes them so special in terms of what we're seeing is that it's a relatively fast change, and it's a very large change in how bright these objects are. So AGN, which are powered by supermassive black holes, normally we see them change in brightness over the course of hours or days or years. And in order for them to change, generally the relation is the longer the time taken for the change, the bigger the change can be. What makes these so special is that we're getting very short, sharp changes. So we're seeing objects get brighter by a factor of 100. So it's becoming 100 times brighter. It happens over the course of an hour of a quarter, and in one object, GSN 69, it's happening every 9 hours. Now, what's really interesting as well is that we actually looked at this particular object about 17 years ago, and we didn't see any eruptions then. The energies that we're seeing are very, very, very high. And currently, there's a typo on my presentation there. The cause is unknown rather than unknown. There are a couple of possible ideas as to what could be causing them. One suggestion is that the way that matter is being accreted onto the supermassive black hole in that disk, it's reaching some sort of limit. So it's hitting the absolute limit for how quickly it can suck matter in, hits that limit and has to slow down for a while. Another possible suggestion is that there is some kind of object, possibly another supermassive black hole, that is smashing through the accretion disk and is orbiting the central supermassive black hole. And another possibility is that there is some sort of object that's orbiting nearby and on an elliptical and oval orbit. And as it gets closer, when it's close to the supermassive black hole can take matter away from that second object, and that's what's fueling these short, sharp eruptions. Okay, hopefully in that I have piqued your interest into black holes and X-ray astronomy. Thank you very much for listening, and are there any questions?
So was I understanding right? So every single black hole has an accretion disk, is that right?
Not necessarily. In terms of how black holes take in matter, the best explanation is that it is through an accretion disk. So if a black hole is accreting, it is through a disk.
Okay. So I mean, basically what was going through my mind is that, so if they have that, then they can't be like invisible. So you have to be able to detect them.
Yes, we should be able to detect most black holes through their accretion disks. It's very unlikely that I guess there would be a black hole somewhere where there isn't matter for it to accrete, because in order for there to be a black hole, it must have been created in the first place. So there must have been something there. I guess the only way that we couldn't see a black hole would be if it had engulfed all of the material that was nearby to it. But that would take a very, very, very long time. Certainly, it's actually one of the sort of questions still around supermassive black holes, is we have no idea how some of them could have been created and be as big as they are, because according to sort of current theories, we don't know how they could have grown as large as they have done. And there's still, whole galaxies surrounding them that they haven't eaten yet.
Luckily for us.
Yeah.
So are we 100% sure that there's a big black hole at the center of our galaxy? Do we know that for a fact?
As certain, rather, we're as certain as we can be, because from what we've been able to see of the object Sagittarius A star, we can't see it in visible light because there's too much gas and dust between us and it, just from sort of gas and dust that's in the galaxy. So we haven't been able to see it directly there. We have been able to see radio transmissions, radio waves coming from it, and the X-rays as well. And as I showed, the motions of those stars moving around means that there must be a very massive, but also very compact object there. Mm. There has to be something there. it has to be quite compact, and from the radiation that it's giving off, the best possible explanation by far is that it is a supermassive black hole.
Cool. Question in the chat. What happens to light when it enters the black hole? Why does it become black?
Ooh, that's a really good question. So, I guess what happens to light when it enters the black hole? Actually, we have no idea, and we have no idea at all, because nothing can escape the black hole. It's just sort of a complete void in space. There's nothing coming out of it at all. Part of the reason why it becomes black actually is due to what's called gravitational redshift. So it's a feature of general relativity that as light tries to move away from a very massive and very heavy object, what it does is it makes the wavelength of the light longer. So in the same way that you have Doppler shifting caused by objects moving away or towards you, gravity has the same effect on radiation. This is, again, part of the reason why we can't see anything coming from the black hole, is that the gravity is so strong that it would stretch the wavelengths of light to, well, essentially infinitely long.